So this is the second lecture of the week, and my goal today is to explain to you what unitarity, or equivalently reflection positivity, means for conformal field theories. So let's get started. Why am I doing this to begin with? So the idea here is I want to use crossing symmetry in the 4-point function to constrain the space of conformal field theories. And this is this notion of the conformal bootstrap. And to do this effectively, I'm also going to need to impose an additional constraint on the CFT, that of unitarity or reflection positivity. So to use crossing symmetry to constrain the space of CFT, we impose unitarity, or equivalently reflection positivity. So these constraints give us a number of conditions on the operator spectrum and also the 3-point functions. In particular, we learn that for scalar operators, the dimension has to be greater than or equal to d minus 2 over 2. For fermions, we learn that the dimension has to be greater than or equal to d minus 1 over 2. For vectors, it has to be greater than or equal to d minus 1. D here is the space-time dimension, so this is vectors. And for symmetric traceless 2 tensors, it has to be greater than or equal to d. So the stress tensor would be an example here. And there are similar constraints for all the different possible representations of the Lorentz group. Let me give you one possible extension of this list of inequalities. We could write, for example, here that delta is greater than or equal to d plus L minus 2 for a symmetric traceless L index or spin L tensor. So that's for the spectrum. And then another constraint that comes from unitarity is that the 3-point function coefficients are real. So another constraint here is that also the C delta i's that we had in the conformal block decomposition, the operator product expansion coefficients or the 3-point function coefficients, if I square them, they have to be greater than or equal to 0. Since the coefficients themselves are real, their squares are positive or at least non-negative numbers. So that's going to be the input for the bootstrap. That's what I'll need to use this notion of the bootstrap in the next lecture. So for the remainder of this lecture, I'd like to explain a little bit where these bounds come from. So let's look at this list to start out with. I want to make a remark about this list. There's something special about the operators that saturate the bound. What are those operators that saturate the bound? Well, we've seen examples of all of them, actually. The free scalar saturates the bound for scalars. The free fermion saturates the bound for fermions. I believe we saw this in the first lecture of this whole module. And then we discussed a little bit also about conserved currents and the conserved stress tensor. The conserved current has a dimension that's d minus 1, and the stress tensor has a scaling dimension which is d. So these are the operators that saturate the bounds. We can go and we can look at the list on the previous slide and we see it, right? We see for the scalar that when the dimension is d minus 2 over 2, that's the free scalar. For the fermion, when the dimension is d minus 1 over 2, that's the free fermion. For the vector, when the vector is conserved, when it's a conserved current, the dimension is d minus 1. For the 2 tensor, the symmetric traceless 2 tensor, when the dimension is d, that's the same as the dimension of the stress tensor, energy per unit volume. For the stress tensor case or for the conserved current, it's charge, which is dimensionless per unit volume. And that's why you get these d and d minus 1 scaling dimensions. So there's a reason for this, of course. All 4 of these operators, they satisfy a condition that some of their descendants vanish, a so-called shortening condition. The multiplet, so these are primary operators, and then the multiplet is the primary plus all its descendants. But then if some of the descendants aren't there, then the multiplet's smaller. So the multiplet, as they say, is shorter. It's a shorter multiplet. So in the free scalar, what's the condition? It's that the Klein-Gordon equation acting on the scalar vanishes. And the Klein-Gordon equation, it's 2 derivatives. It's 2 actions of momentum operator, of the raising operator that creates the descendant states. That has to vanish. Similarly, for fermions, the Dirac equation has to be satisfied. So again, it's a derivative acting on the spinor, must vanish. That's a shortening condition. For the conserved current, it's the fact that the divergence of the current vanishes. And for the conserved stress tensor, it's that the divergence of the stress tensor vanishes. So in all of these cases, some combination of momenta acting on the operator vanishes. There's a shortening condition on the multiplet. So I think I just wanted to point out that interesting fact about the operators that saturate the bound. So now what I'd like to do is I'd like to try and understand where those bounds come from. So I want to start by talking about reflection positivity. So the idea here is I have some plane of reflection in my flat space. So I'll draw that as a line here. And on one side of the plane, I insert some collection of operators. Maybe I have one here at x1, another at x2, another here at x3. And then on the opposite side of the plane, I have the reflected guys. Hope I can do justice with my drawing skills. So this would be the reflection of point 1, the reflection of point 2, and the reflection of point 3. So if I have some composite operator, let's call it calligraphic O, which is a product of these phi 1 at x1, phi 2 at x2, phi 3 at x3, I can also think about the reflection of that operator, where I insert all of those points on the other side of the plane. So this would be phi 1 of r of x1, phi 2 of r of x2, and phi 3 of r of x3. The statement of reflection positivity is the following. Reflection positivity says that the following correlation function, r of O with O, is greater than or equal to 0. I mean, it doesn't have to be 3 operators. It could be as many operators as you want, but you choose some operator O, some generalized composite operator O, you reflect it, you put both guys in the correlation function, and the claim is that if the theory is reflection positive, this quantity must be positive or 0 for any O. Now, why do people care about this? Well, there's a theorem, it's called the Osterwalder-Schrader reconstruction theorem, which I don't really want to get into. It's a part of constructive field theory. But the idea behind this is that you need reflection positivity in a Euclidean setting for a QFT in a Euclidean background where time is just like all the other spatial coordinates, to have unitarity in the Lorentzian one, where you continue time into a complex direction, where you send t to I times t, and then have a true time-like coordinate. So in order to have unitarity in this situation where you have a Lorentzian spacetime or a Minkowski spacetime, you need reflection positivity and the associated Euclidean setting. So actually, when I say unitarity, then what I really mean is just reflection positivity, because I'm not really going to be interested for the rest of this discussion in Lorentzian CFT. I'm going to be interested in Euclidean CFT, where time is just like all the other coordinates. Our focus here is Euclidean. And so I'm going to couch all my arguments in terms of reflection positivity. Okay, so let's keep going with this. The next statement is that since I'm in CFT, planes in CFT are the same as spheres. Now, why do I say that? Well, let's draw some pictures to try and convince you. This is one of the exercises in the notes, and so I leave you to work out more of the technical details yourself, but I hope I can just convince you by drawing a couple of simple pictures. So claim 1. So here's my Euclidean spacetime. I'm just going to draw 2 of the dimensions, x and y, and I have my plane of reflection here. I could set it here at x equals 1 if you wish. And now what I'm going to do is I'm going to act with it with a special conformal transformation and see what happens to the plane. So here's x and y. Maybe I should call them x prime and y prime since they're transformed. I'm going to do a special conformal transformation with a particular value of this b vector. I'm going to set the v vector equal to 1 in the x direction and 0 in all the others. And when I do this, I'm going to find that that plane at x equals 1 becomes a sphere centered at the origin with radius equals 1. That's what the special conformal transformation does to planes. It sends them to spheres. So I've left you to work out the details as an exercise. It's not a very hard one, but I think it's a gratifying one to see a little bit in more detail what these special conformal transformations do. Now the second claim, which is part of the same exercise, so let's just copy these. So now I have 2 copies of the same diagram. And I want to examine what happens to the reflection under this map. So say I have a point here, and I know that under reflection, it will become the point on the other side of my mirror. This is what reflection does. Now, what's sort of interesting here is that after the special conformal transformation, maybe I have the new point, it's outside, and the corresponding reflection map after the special conformal transformation turns out to be an inversion. That reflection, what I had before was reflection, after the special conformal transformation becomes the inversion map. So that's the other part of this exercise. So given that, let's go to our cylindrical coordinate system that we were using for radial quantization. So we have our line element, we have our radial coordinate, which we expressed as a kind of a time, e to the 2 tau d tau squared, and then plus all of the angular coordinates, which I've grouped together in this funny d omega squared symbol. So here, I mean, we used to have an r, which is now e to the tau, and so r greater than or equal to 0 corresponds to tau running over all possible real values. Right, I hope you all remember this from the radial quantization lecture a few weeks ago. So what does reflection positivity mean after special conformal transformation when I've transformed my plane now to a sphere? So reflection positivity means that I can call it now a kind of a time reflection of my operator O with O. This is what has to be greater than or equal to 0, where what I mean by this operation T is that it sends tau to minus tau, or equivalently r to 1 over r. This was inversion, right? This is what I called I on the previous slide and in previous lectures. This time reversal is the same as the inversion operation on the sphere. So I can equivalently think about reflection positivity as a statement about this time reversal in my cylindrical coordinate system. Okay, so we have this notion of reflection positivity in terms of time, or this Euclidean version of time tau, which is actually a radial coordinate. And I'll just mention in passing that we can make the connection with unitarity a little bit more precise here. You know, if we send tau to it, this is called a Wick rotation. There's a sense in which, you know, restoring the Lorentzian nature of time, or the Minkowski nature of time, there's a sense then in which I can think of this time reversal as the dagger operation, as the Hermitian conjugate. Because, you know, now instead of sending t to minus t, I can also think of just taking the complex conjugate of the square root of minus 1, which sends it to minus it. Okay, so we're almost there. I want you to bear with me a little bit longer, and we'll get to the punchline soon. The next thing I want to think about is how this notion of time reversal or reflection positivity acts on momentum and special conformal transformations. So I want to think about p mu and k mu. So if you remember from a while back when we developed the representation theory of the conformal group, we compared it to the harmonic oscillator, and we said there was a sense in which P was like the raising operator because it generates these descendant states from the primary state. The primary state was like the lowest energy state of the harmonic oscillator. The descendant states were like excited states of the harmonic oscillator. And then K is like a lowering operator. So there's a sense in which they're Hermitian conjugates. And so it's then natural to ask, well, maybe there's also a sense in which they're time reversals of each other in this new CFT setting. And that's indeed the case. So let's work that out. So if I write down I p mu, I can write that as just partial mu. I've absorbed the I. And now by the chain rule, what I want to do is I want to express that in my new cylindrical coordinate system. So let's write our cylindrical coordinate system down. I have x mu, which is e to the tau, that's the radial coordinate, times our angles. I'll just write that as a unit normal vector n mu. And if I invert that, then what do I have? I have tau is 1/2 the log of x squared, by which I mean x mu upper contracted with x mu lower. And n mu, I can write that as x mu over the square root of x squared. Okay, so let's use the chain rule here. So I have my partial derivative. I can expand that out. In my new coordinate system, I can write that as d tau dx mu d tau plus dn nu dx mu ddn nu. I guess possibly by some slight abuse of notation here, but I hope you see what I mean. So now I'll just I'll take my derivatives. I'll use my result here and see what happens. So when I take d tau dx mu, I'm going to get x mu over x squared dd tau. And then when I take the x mu derivative of n, I'm going to get two terms. Well, first I can take a derivative of the numerator. That's going to give me a Kronecker delta function. I mean, I could write the Minkowski tensor, but I'm in this Euclidean context here where time is supposed to be like all the other spatial coordinates. So it's just the Kronecker delta divided by the square root of x squared minus, and now I take a derivative of the denominator and I get x mu x nu over x squared to the 3/2, and now d dn nu. And now what I'm going to do is I'm going to try and re-express that in terms of our tau and mu variables. So I'm going to pull out a 1 over absolute value x. That's the same as e to the minus tau. And then what's left inside? Well, I have an n mu dd tau, and I have a Kronecker delta function, and I have these unit normals, n mu and nu, and I have a partial d dn nu, where there's this implicit sum over the nu index. When I have, a lower nu and an upper nu, I've got to sum over them. And if I have a lower nu downstairs, that's like an upper nu. So I've got to sum over the nu indices. Okay, so that's for P. And now what I'll do is I'll leave as an exercise. It's a little bit grungier, but we've already done the hard work. You can use actually this result to help do the next result for the special conformal transformations. You can just plug that result in. So for ik mu, well, we saw a few lectures ago, I can write that as x squared d mu minus 2x mu x dot partial. And now if I do my change of variables, I can write it in my cylindrical frame as e to the tau minus n mu d tau plus, and then the same term we had before, delta mu nu, n mu n nu, d dn nu. Okay, so now I'll let you stare at that for a couple seconds on your own, but you should see something. You should see how the dependence on tau changes. So up here we have a minus tau, where here we have a plus tau. Here we have a plus dd tau times this unit vector. Here we have a minus dd tau times this unit vector. And so the statement I want to make here is the following, that this calculation has shown that if I take the time reversal of I p mu, I get I k mu. And I've included these extra factors of I because I don't want to think about how I changes under time reversal, whether there should be some extra complex conjugation there or not. I've tried to write everything as implicitly or explicitly real quantities. So I don't have this extra complication about what to do with complex numbers inside the inner product. At any rate, so I have this condition on I p mu and I k mu. We're ready now for the payoff. I'm glad you followed me this far. It's just going to be a little bit longer, and we'll see how all of these bounds come out. So consider a conformal primary state, phi I, and the claim is that if I take following correlation function or inner product of I k mu, I p nu, phi j, that this should be positive definite. That's the statement of reflection positivity. All right, so let's see what the consequences of this are. We can use our knowledge of the conformal symmetry algebra to simplify this expression a bit. Well, let's pull the i's outside. That gives me a factor of -1. I've got a phi I prime. I can write a commutator of k mu p nu with phi j, but now I have an extra term that I have to cancel, so let's subtract that off. Let's subtract off phi I prime p nu k mu acting on phi j. This is still positive. I haven't done anything, just written it in a slightly different way, added and subtracted the same term if you like. And now here comes something interesting. These are conformal primaries, right? So they're annihilated by the special conformal transformation. So this second term is actually just a big fat zero. And I'm just left with a commutator, and I can go back to my algebra and plug in for the commutator and see what happens. So I'm going to learn then that minus 2I phi I prime eta mu nu dilatation minus Lorentz phi j, that this is greater than or equal to 0. And this is the basic result from which all of those unitarity bounds on the spectrum follow. Because these conformal primaries, they're eigenstates of dilatation, so we can automatically plug in the conformal weight and try and find some bound on the conformal weight based on the largest possible eigenvalues of the Lorentz generators. Let's do it one by one, right? Let's consider a scalar. Let's do the simplest case. Actually, it turns out not to be the simplest case for reasons we'll see in a minute. Let's consider a scalar. Now for a scalar, the Lorentz generators just annihilate the conformal primary, and D acting on phi, because there is no index, right? This J isn't there, so let's just cross it out. not really there. It's just a scalar. And d acting on phi is going to give me I delta times phi, the weight of that primary state, whatever it may be. So d is the operator, and then delta is this number, this C number. So I plug that in to what goes above, and I'm going to learn that, assuming the inner product is positive, it should be its reflection positive, it should be positive. I learn that delta is greater than or equal to 0. Great, so there's our first bound. Now, if you've been paying attention, this looks a little bit wrong, because what I told you a few slides ago was not that it was greater than 0, was that it was greater than d minus 2 over 2, was greater than the dimension of the free scalar, not greater than 0. It's only going to be 0 when d equals 2. So what happened? Well, in fact, I have to be able to allow the delta equals 0 operator. That's the identity operator, and we've used that already. You need it to be able to write down a two-point function, in fact. So that has to be in the spectrum. What the statement I meant to say more precisely earlier on is that there's then a gap, and that after the identity operator, the spectrum is bounded below by d minus 2 over 2. So except for the identity operator, delta is greater than d minus 2 over 2. And where does this come from? Well, this is an exercise for you. It's a nice exercise that will use your knowledge of the conformal symmetry algebra. We can consider a slightly more complicated correlation function. We insert a k squared and a p squared, and we take the inner product with these two conformal primaries. And again, these are scalars, so let's cross out the Lorentz index. The claim is that this being greater than or equal to 0, now I have 4 of these square roots of minus 1, so they all multiply together to give 1. So this thing actually has to be greater than 0 as opposed to less than 0. So if you work out this exercise, you're going to find that delta times 2 delta plus 1 minus d is greater than or equal to 0. So it's actually a quadratic constraint that removes everything between dimension 0 and the dimension of the free scalar, and then allows everything above that. Now, for the higher spin operators, the constraints are a bit simpler. We can just go back to the result we had before. So for vectors and spinors, let's return to this constraint minus 2i phi I prime. So now the index does mean something. It's either going to be a vector index or a spinor. Minkowski minus m mu nu phi j greater than or equal to 0. And I see I really have, it's so hard to keep these lectures error-free, and I see I've been making a mistake all this time. I've been putting in the Minkowski tensor, and I really don't want to do that. I'm working in the Euclidean context, right? So I shouldn't have this Minkowski tensor. What I should really have there, of course, is the Kronecker delta. So let's put that in there. Okay, sorry for that. I think it's been littering my slides for the past few minutes now, but it really should be a Kronecker delta function in there. Good. So we'll start with this, and then what we're going to do is we're going to use the explicit form for the Lorentz generators that we had from the lectures in the first week. We wrote down, it was another exercise, we wrote down the Lorentz generators for vectors. So they're going to have these vector matrix indices, I delta mu rho, delta lambda nu, minus I delta lambda mu, delta nu rho. This was for vectors. And then we also had a result for spinors. So we have a spinor index, alpha, and another spinor index, beta. We can write that as minus I over 4. Gamma mu, gamma nu. We have these gamma matrices in the exercise, minus gamma nu, gamma mu. And these have these indices, alpha, beta. So this was for spinors. So go ahead and you plug that back in. This is an exercise, a last exercise. You can then show from using these explicit forms for the representation that delta is greater than or equal to d minus 1 for the vectors, and delta is greater than or equal to d minus 1 over 2 for the spinors, which were the bounds we had on the first slide from this lecture. And you can go on, of course. I mean, if you want to use a little bit more sophisticated representation theory, you can deal with all the possible representations of the Lorentz group at once. You then have to express your result in terms of Casimirs, but I think this is enough. You get the idea. We'll stop here. So before closing this lecture, I have a remark or two. You might wonder about further constraints that come from looking at higher powers of these special conformal and momentum operators. K to some power m, p to some power m. Of course, it has to be the same power or it's not going to be reflection symmetric. But these do not seem to give further constraints. The bounds we looked at, either the lowest order bound for everything but scalars, or the lowest bound plus the quadratic bound for the scalars, gives you all that you're going to get. The story is a bit different. The story is a bit different for theories with larger symmetry algebras. It turns out if the theory is also supersymmetric, or if you're working in the context of two-dimensional conformal field theory, you can get a lot more mileage from these kinds of considerations. In fact, there's a very nice discussion in two-dimensional conformal field theory where you can derive essentially all of the minimal models from reflection positivity of the algebra acting on these primary states. Okay, but we'll leave it there. And next time, with these bounds in hand for the operator spectrum and the three-point functions, we'll go on and think about what the bootstrap means in conformal field theory.